Simulations show how the impact of an asteroid may have strengthened the Moon's weak magnetic field early in its history. NASA's Apollo missions brought lunar rock samples to Earth for study. Over the decades, a lot of information has been obtained from these rocks, but one mystery remains. Many of these samples show signs of exposure to strong magnetic fields similar to Earth's magnetic field, while today the Moon has no such field. So, how did these lunar rocks become magnetized? Numerous efforts have been made to explain the magnetic rocks on the Moon. The latest theory proposed by MIT scientists suggests that a large asteroid collision temporarily strengthened the Moon's weak magnetic field in its early days, and this sudden change is recorded in some of the lunar rock samples. Spacecraft observations, along with results from China's Chang'e 5 and Chang'e 6 missions announced earlier this year, are mostly consistent with the existence of at least a weak magnetic field in the early Moon. But where did this field come from? Magnetic fields usually form in planetary bodies due to a process called dynamo mechanism, where molten metals in the core begin to convect as they gradually lose heat. The problem is that the small core of the early Moon had a mantle that was only slightly cooler than the core, meaning significant convection would not have occurred to create a strong dynamo. Several hypotheses have been proposed regarding how a central dynamo could have formed in the Moon. For instance, an analysis in 2022 suggested that during the first billion years, when the Moon's surface was covered in molten rock, giant rocks formed as the magma cooled and solidified. Heavier minerals sank toward the core, while lighter materials formed the crust. The authors of the study argued that over time, a layer of titanium formed just beneath the crystalline surface, and since this layer was denser than the lighter minerals below, it eventually broke into pieces and sank down toward the mantle, a phenomenon known as gravitational overturn. The temperature difference between the cooler sinking rocks and the hotter core caused convection, which periodically generated strong magnetic fields. This process might explain why some lunar rocks exhibit magnetic effects while others do not. However, the presence of a dynamo-induced magnetic field may not be necessary at all. For instance, authors of a study from 2021 suggested that previous analyses of lunar samples could have changed during the testing process. Their heated samples from the Apollo 16 mission in 1972 using CO lasers to prevent alterations in the magnetic-bearing materials. They concluded that any magnetic effects in those samples could be explained by impacts from meteorites or comets on the lunar surface. In 2020, two authors of the new paper, Benjamin Weiss and Rona Oren from MIT, conducted simulations to address the mystery: could a massive impact be the source of plasma that strengthens the weak lunar magnetic field generated by the Sun? Enough to explain the recorded magnetism in lunar rocks? The results at that time seemed to reject this possibility. This time, the researchers returned with a new hypothesis that actually combines elements from both the dynamo and plasma-producing impact theories, while also considering the shockwave effect from the impact. To test the new hypothesis, they focused on an impact on the scale that formed the Imbrium Basin on the Moon, as well as simulations of plasma clouds. Their initial assumption was that the early Moon had a dynamo that produced a magnetic field approximately 50 times weaker than Earth's. Results showed that a large impact, such as from an asteroid, could create a plasma cloud, some of which dispersed into space while the remainder flowed to the far side of the Moon, temporarily enhancing the existing weak magnetic field for about 40 minutes. The key factor in the magnetic field enhancement process was the shock wave from the initial impact. This shock wave resembles seismic waves and rattled the surrounding rocks in such a manner that their subatomic spins aligned with the newly enhanced magnetic field. Weiss likened this effect to throwing a deck of 52 playing cards into the air within a magnetic field. If each card had a compass needle, its magnetism would reorient upon hitting the ground. Scientists hope that future crewed missions from NASA and the Artemis program can help solve this mystery, as returning samples is one of the main objectives of these missions.